Part winding reduced voltage starter calculations. In this presentation, we're going to be looking at the inrush current value, starting torque, current on the line and load side of the starter, voltage on the line and load side of the starter, and overload sizing for a part winding three-phase motor starter. In order for us to accomplish this, we need to work with some baseline numbers, and those baseline numbers need to be from a standard full voltage starter. We're going to use the values here from the same full voltage starter that we used in the full voltage starter tutorial. If you're unsure as to how we got these, go check out that tutorial. So we have a skim motor, 600 volt three phase 12 lead, and this motor has a 27 amp FLA due to a parallel delta connection. Its inrush current on full voltage start is just over 134 amps, and its torque for full voltage starting is just over 223 foot-pounds. Let's take a look at how this is going to work with a part winding starter. Now keep in mind, a part winding starter is only going to energize exactly half of the motor at start. And this happens to really simplify our calculations. That's because we can simply take the inrush current value of a full voltage start and divide it by 2. And so with 134.71 amps divided by 2, we end up with 67.35 amps inrush current. The torque value is actually extremely simple, and that's because the torque value is exactly half, because there's only half of the motor energized. 223.8 divided by 2 ends up giving us 111.9 foot-pounds of torque. Now, what about the current that we would expect to see on both the line and the load side of the motor? Well, here's our basic motor. And often when we're doing troubleshooting, if we have an MCC, which we'll take a look at in this program, we don't have access to the line side of the starter, not readily. Might be far easier for us to simply access the load side of the starter, all of those conductors. Now there's 6 conductors, so we should have a general idea as to what to expect. When this motor is running in start, we would expect to get exactly the same value of current on 3 of these line conductors here and over here. So these conductors, we would end up getting 67.35 amps, and the 3 conductors down here, which are connected to the start portion of the motor, those would each have 67.35 amps also. Now, what about during run? Because during run is a little bit different. During run, we actually have 2 windings connected in parallel. And so during run on the line side of the starter, we would expect to get FLA, no question. However, on the load side, all 6 of these conductors will each carry exactly half of the FLA value. 27 divided by 2 gives me 13.5 amps, and that's because of this simple diagram here. We have a delta and delta, and they are connecting over. They're identical in every way, meaning that this current here of 13.5 will add with another value of 13.5, which would be coming off of this half of the motor. They'll combine at the junction, and Kirchhoff's current law dictates that the total should be the addition of those 2 values. So 27 amps would be on the line. Remember, the line side, 27.5, is after the starter. Well, what about the voltage then? Well, the voltage is a little bit different also, and if we wanted to validate at all that the motor starter was functioning properly, perhaps we want to use our voltmeter. Now, you do have the choice of the line or load side, but consider for a moment, would we be anticipating any difference of voltage? Now, during start, of course, there will be 3 conductors that have 0 volts on them, but we're kind of negating that at this point. It's assumed that they would have 0 volts. The other 3 would be the side that is energized with just the 3 conductors going to half the starting portion of the motor, and the line voltage would be exactly the same on both sides of the starter. What about when we transition to run? The line voltage would not change at all, would it? And although this motor is known as a reduced voltage starter, in reality, it's not really reducing the voltage at all. The last item we want to look at is the overloads. Now, the overloads are going to be sized at all times based on the actual current flowing through them during run. In a part winding motor, the FLA divided by 2 would be the amount of current that we would expect to see flowing through the overload heaters themselves. And the code accounts for this in a subrule within 28306, where it says people should be aware that the current flowing through the overloads may not necessarily be the FLA. This means that the maximum overload value is going to be calculated by taking the FLA divided by 2 and then multiplying it by the multiplier given in 28306. Now, since this motor is exactly the same as the previous tutorial, that means that the multiplier is 1.25, and we end up with a maximum overload of 16.87 amps.